Hi there, and welcome to this special edition of Under the Microscope. I'm your host, Pranoti Kshirsagar, and today we are trying something new and exciting. In these AI-generated episodes, we offer you a quick dive into the fascinating research discussed on our show. Thanks to Google's NotebookLM, the experiment version, the AI crafts both the script and the voice you will be hearing. While this summary gives you a taste of our full episode, I would highly encourage you to check out the full conversation between myself and the guest, where we dive deep into the science and the stories behind the research. Find the link in the description and enjoy the best of both worlds, the AI efficiency and human connection.
Ready for a deep dive into a world where tiny particles hold the keys to incredible technological leaps?
I'm ready. Where are we headed today?
Well, today we're going beyond your typical lasers and photons, venturing into the mind-boggling realm of electron spins.
Sounds intriguing. I know we've had a lot of requests from our listeners to dig deeper into quantum communication and sensing.
You read our minds, and we've got a real treat. We're dissecting a fascinating interview with Dr. Mete Atature, a true pioneer in the field.
I'm following his work for a while now. He's doing some seriously groundbreaking research, pushing the boundaries of what we thought was possible.
Right. It's like he's leading the charge into this new frontier of quantum technologies, and we're all just trying to keep up. But before we get ahead of ourselves, let's take a step back for those who might be new to this world. We often hear about quantum communication relying on photons, those speedy particles of light.
Ah, yes, photons. Those are essential players in this quantum game.
They are. But what makes them so special for transmitting information? What's the secret sauce?
It all boils down to a fundamental principle of quantum mechanics. You simply cannot observe a photon without messing with its state. It's like trying to catch a snowflake on your tongue. The moment you try to observe it directly, it melts away.
So it's all about maintaining that pristine quantum state even while transmitting information.
Precisely. And because any attempt to eavesdrop on a message encoded in photons would disrupt their state, it'd be immediately obvious. Like, imagine trying to peek at a birthday present but accidentally ripping the wrapping paper in the process. You can't exactly put that back the way it was, can you?
Sneaky photons, always maintaining their security. But Dr. Atature's research adds another layer of complexity by bringing electron spins into the mix. He talks about these things called quantum dots. What are those exactly?
Think of a quantum dot like a tiny box, so small you could fit billions of them on the head of a pin. We're talking nanoscale here.
Okay, I'm picturing something incredibly tiny, but what are they made of? What's the material?
These dots are typically made of semiconductor materials, and they can do some pretty remarkable things. Not only can they generate single photons on demand, like a tiny flashlight that emits one photon at a time, but they can also trap a single electron inside.
So we're essentially trapping a single electron inside this tiny semiconductor box. What happens to the electron inside?
Here's where it gets even more interesting. That trapped electron has a property called spin, which you can picture as a tiny compass needle. And just like a compass needle can point north or south, an electron spin can point up or down, representing a 0 or a 1 in the quantum world.
Okay, I'm trying to visualize this. We have this tiny compass needle trapped inside an even tinier box. That's mind-boggling. But how do we go from there to actually using them for communication?
That's where the real magic happens. Dr. Atature and his team have figured out how to entangle the photon and the electron within a quantum dot.
When we say entangled, what do we really mean? Are they literally tangled up like a pair of headphones after a trip in your backpack?
Not quite. We're talking about a connection so deep, so bizarre, that the states of those two particles become intertwined. Measure the state of one, and you instantaneously know the state of the other, no matter how far apart they are.
Hold on a minute. We're talking about two particles linked across potentially vast distances. If you change one, the other changes instantly, like some sort of telepathic connection. How is that even possible? Is this like they're sending secret signals faster than the speed of light?
That's the thing about entanglement. It's one of the biggest head-scratchers in quantum mechanics. It's not about information traveling faster than light. It's about these particles sharing a special connection, a shared fate that just doesn't make sense in our everyday classical way of thinking. Imagine flipping two coins that are linked in this way.
Okay, so two coins that are linked, entangled. I'm picturing it. Go on.
If one lands on heads, you instantly know the other landed on tails, even if they're miles apart. It's as if they were always meant to be mirror images of each other, even when separated.
Okay, my brain is definitely bending a little bit, trying to wrap itself around that. So these two particles, once entangled, become two parts of a single system, no matter how far apart they are. But how do we actually use this for communication? What's the practical application here?
Imagine you're here, and Dr. Atature is in his lab in Cambridge. You each have an entangled photon-electron pair. He sends his photon across the globe to you, carrying specific information encoded in its state. But instead of directly reading the photon, which can be risky over long distances, you transfer the information onto your electron. Now your electron, right here, and his electron, all the way in Cambridge, are entangled, forming a secure link, a node, in a potential quantum network.
It's like playing a high-stakes game of quantum telephone, passing information through this inviolable link. But realistically, what happens if that photon gets lost along the way? I mean, we're talking about sending these things over huge distances. Surely some of them must go astray, right?
That's the catch. It's like sending a message in a bottle. You can't be sure it'll reach its destination. Photons, even though they're zipping around, they can get lost or absorbed, especially over long distances.
So how do we overcome this challenge? I mean, we can't exactly tie a string to a photon and reel it back in.
No strings attached in the quantum world. But Dr. Atature has an ingenious solution. Quantum repeaters.
Quantum repeaters. Now, those sound interesting. Is it like having a team of microscopic postal workers making sure our photon reaches its destination?
It's a clever analogy, but think of it more like a relay race. Instead of one runner trying to cover the entire distance, imagine a chain of runners strategically positioned along the way.
Okay, so instead of tiring out our single photon, we have these repeaters as pit stops along the way, making sure the information gets passed on.
Exactly. Each repeater is essentially another quantum dot, like the one we discussed earlier, with its own entangled electron pair.
Right, those tiny boxes with the compass needles inside.
Exactly. So the repeater receives the incoming photon, carefully transfers the encoded information to its own entangled electron pair, and then generates a brand new, fresh photon carrying the same information to continue the journey.
It's like hitting the refresh button on the signal without ever actually copying it, right? Because we can't mess with those quantum states or everything falls apart.
Exactly. We're playing by the rules of the quantum world here. But here's the best part. These repeaters aren't just relay stations. They act as security checkpoints for the entire network.
Security checkpoints. Tell me more.
Because each repeater has its own entangled pair, we can continuously monitor the entanglement between every point in the chain. If someone tries to intercept a photon mid-transmission, trying to eavesdrop on our quantum conversation.
Trying to steal a peek at the message.
Exactly. The act of eavesdropping would disrupt the entanglement, like tripping a silent alarm, alerting the entire network.
Wow, it's like each repeater is a tripwire, protecting the quantum message as it travels along. That's incredible. It seems like we have an amazing level of control and precision over these electron spins. But is it limited to communication? Dr. Atature also mentions sensing applications.
You're right, the versatility is astounding. It's not just about sending messages. These electron spins can also be used to probe the world around us in incredibly precise ways.
What kind of sensing are we talking about here? Give us some examples.
One fascinating example Dr. Atature talked about is the nitrogen vacancy center in diamond.
Nitrogen vacancy center? That sounds complicated.
It's simpler than it sounds. Imagine a perfect diamond, but with a tiny flaw. A single missing carbon atom replaced with a nitrogen atom. Next to that nitrogen atom is an empty space, a vacancy. That specific defect, that nitrogen vacancy, or NV center, well, it turns out that's a gold mine for quantum sensing.
Okay, so a flaw in the diamond is actually the key. Sounds counterintuitive, but go on.
It's all about perspective. This NV center acts like a super-sensitive magnetic field sensor, and we can actually read out its measurements using single photons.
Hold on. So we have this flawed diamond, which, thanks to the magic of quantum mechanics, becomes this incredibly sensitive sensor. That's pretty cool. But what's the practical use?
Well, Dr. Ature's team is taking these NV centers, embedding them in tiny particles called nanodiamonds, and using them to study biological systems.
Nanodiamonds. So we're talking about incredibly tiny diamond sensors. Where would we even use something like that?
Imagine a microscopic diamond sensor. So small it can be inserted into a living cell, capable of measuring things like temperature, pH, even the motion of molecules, all in real time.
It's like having a microscopic spy sending live updates from within a living cell. It's mind-boggling to think we can now observe these incredibly tiny systems without destroying them. But how do we even get these nanodiamonds inside cells? Do they just slip in unnoticed?
It's all about stealth. If you prepare the surface of a nanodiamond carefully, making it pristine and clean becomes incredibly inert. This means the cells don't really see it as a threat, more like a harmless speck of dust. And they readily take up these nanodiamonds without much fuss.
So the cells just kind of welcome the nanodiamond in. No alarms, no immune response, nothing.
Pretty much. They just go about their business.
Yeah.
But here's the truly exciting part. By having these nanodiamond spies inside living cells, we can start to unravel some of the biggest mysteries in biology.
It's like opening up a whole new window into the inner workings of life itself. So what kind of things are we hoping to learn from these tiny spies?
Imagine mapping neuron activity in the brain with incredible detail, understanding how diseases like cancer develop at the cellular level, even developing new diagnostic tools with unprecedented accuracy. We're talking about a revolution in healthcare.
This is incredible. It's like we're no longer passive observers, but active participants in the intricate dance of life itself. But going back to those electron spins, we talked about how their spin can represent a 0 or a 1, like a computer bit. Could this be applied to computing itself?
You're on the right track. Remember how we talked about qubits, the building blocks of quantum computers?
Mm-hmm.
Well, it turns out that electron spins, with their ability to be in a superposition of states, could be the key to unlocking the power of quantum computation.
Okay, you're going to have to remind me, what exactly is superposition again?
Imagine flipping a coin, but instead of landing on heads or tails, it lands on both at the same time. That's superposition in a nutshell. A qubit can be in a state of both 0 and 1 simultaneously, at least until we try to measure it. It's like it's in a state of quantum indecision.
My brain is definitely doing backflips trying to picture that, but I think I'm following. So these electron spins, in their superposition state, can act as qubits. But why electron spins specifically? What makes them such good candidates for building these futuristic quantum computers?
Well, it's like comparing athletes, right? They each have their strengths. Electron spins bring some unique advantages to the quantum computing world.
Okay, so what makes electron spins the star players in this quantum game?
First off, they've got stamina. We're talking long coherence times, meaning they can hold on to that quantum information, that delicate superposition state, without getting disrupted by the environment.
So they can run the quantum marathon without collapsing.
Exactly. But it's not just about endurance. They're also incredibly well-behaved.
Well-behaved? What do you mean?
We can actually control them quite effectively. Using things like magnetic fields and light, we can manipulate their spin states, flip them between 0 and 1, even entangle them with other spins. It's like we're choreographing a quantum dance.
So we've got these incredible dancers, but how do we get them to perform together? Building a powerful quantum computer would require controlling not just 1 or 2, but thousands, maybe even millions of these entangled electron spins all working in perfect harmony. How do we scale this up?
That's the million-dollar question, isn't it? It's one thing to choreograph a solo, but a massive synchronized performance with thousands of dancers, that's a whole other ballgame.
So where are we now? Are researchers still struggling to get those first few spins to move in sync, or are we starting to see some actual choreography emerge?
We're making progress. Some researchers are exploring ways to trap arrays of electrons on the surface of superfluid helium, which is this bizarre, frictionless liquid. It's like creating a perfectly smooth dance floor for our electron spins.
No friction, so the spins can glide effortlessly. I like it. What other approaches are there?
Others are using semiconductor materials to build what we call artificial atoms, essentially tiny containers for these electron spins, giving us more control over their behavior.
So we're designing the perfect stage, tailoring it to the needs of our electron spin performers. But even if we perfect these techniques, realistically, how far away are we from quantum computers that can solve real-world problems? Are we talking years, decades, or is this still in the realm of science fiction?
It's hard to say for sure. Some quantum technologies, like those secure communication networks, are already being tested in limited settings. But a universal quantum computer, one that can tackle really complex problems like cracking today's toughest encryption or designing entirely new materials, well, that's probably still a decade or more away.
So we need to be patient. It's a waiting game. But those nanodiamond sensors, Dr. Atature, made it seem like those are already making waves in research labs. Are they closer to practical applications?
Absolutely. Because they're biocompatible and relatively easy to produce compared to a full-blown quantum computer, these nanodiamond sensors could have a real impact in fields like medical imaging and diagnostics much sooner.
It's exciting to think we could have these microscopic quantum sensors revolutionizing healthcare. But there must still be some challenges. What are some of the hurdles that researchers are trying to overcome?
One of the big ones is sensitivity and reliability. These sensors are already incredibly precise, but we need to make sure they can function flawlessly in complex environments like the human body.
So it's not enough to have great dancers, they need to be able to perform flawlessly, no matter what the stage throws at them.
Exactly. We need to make sure our quantum skies can operate undetected, even amidst a flurry of activity. Another challenge is figuring out how to scale up production. Right now, we can make these things in labs, but for them to be truly impactful, we need to produce them on a much larger scale and affordably.
It always comes down to cost, doesn't it? Building a better mousetrap is one thing, but making it accessible to everyone, that's the real challenge.
Exactly. And that's why collaboration is so crucial. Scientists, engineers, industry leaders, we all need to work together, share our knowledge, pool our resources, if we want to see these technologies truly flourish.
Well, this has been a wild ride. We dove headfirst into the world of electron spins, explored quantum communication, peeked into the future of healthcare with nanodiamond sensors, and even caught a glimpse of the mind-boggling potential of quantum computers.
It's clear that the quantum revolution isn't some distant fantasy. It's happening right now, all around us. And it's only going to get more exciting from here.
It's a future filled with possibilities. So until next time, remember to embrace curiosity, never stop asking questions, and who knows, maybe one of our listeners will be the next pioneer to make a quantum leap in this incredible field.
I hope you enjoyed this AI-crafted glimpse into the world of Under the Microscope. To dive deeper into the full conversation, click on the link in the description and join me and my guest for an insightful journey through science. And while you're at it, don't forget to follow Under the Microscope podcast wherever you're listening. And if you're feeling extra generous, leaving us a review would mean the world to us. It helps us bring the science to an even broader and wider audience. Best of all, it's absolutely free for you, but it means a lot to us. Thank you for listening and see you in the next one.